This figure shows the electromagnetic spectrum, including the ultraviolet visible region, which will be covered in another unit in this course. In the following slides, we'll discuss infrared spectroscopy, specifically the absorption of light in this range from 2.5 micrometers to 25 micrometers. Several decades ago, chemists adopted the convention, instead of using wavelength lambda, to use the wave number, which is new with a tilde, and in units of reciprocal centimeters. In my opinion, it is the stretching frequencies that are most useful, and particularly at wave numbers above 1600 reciprocal centimeters. The reason being that there are many overlapping vibrations at lower wave numbers. Stretching frequencies are affected by differences in atomic mass, as you can see for the hydrogen-oxygen bond, which has a high stretching frequency, slightly lower stretching frequency for carbon-hydrogen bonds, and for deuterium-carbon bonds, where the difference in atomic mass now from 2 for deuterium to 12 for carbon shows up as a lower frequency. Stretching frequencies are also related to bond strength, which is inversely related to bond length. This is quite apparent for hydrocarbons in that the sp hydrogen carbon bonds are stronger than sp2 or sp3 hydrogen carbon bonds, with the corresponding decline in frequencies from sp to sp2 to sp3 hybridization. The remaining slides show infrared spectra, primarily from the textbook, which will exemplify various structural features. The first compound is dodecane, which exhibits sp3 hybridized carbon-hydrogen stretches in the region just below 3000 wave numbers. The methyl group has slightly stronger CH bonds than sp3 methylene CH bonds. The methyl group therefore shows up as a pair of stretches, one asymmetric stretch at 2950 and a symmetric stretch around 2870. And likewise for the sp3 hybridized CH2, carbon-hydrogen bonds have an asymmetric stretch 2922 and a symmetric stretch at 2853. Compare this with 1-dodecene, which now has some sp2 carbon-hydrogen bonds. These are very slightly shorter and a bit stronger with bond association energies, and that shows up in a stretching frequency that is just above 3000 wave numbers, just to the left of 3000 wave numbers. There are two numbers that are particularly important in infrared spectroscopy. The first one is 3000 wave numbers for the cutoff between sp2 and sp3 hybridized carbon-hydrogen bond stretches. If we examine the infrared spectrum of one heptine, you will see the sp3 hybridized CH stretches just below 3000 wave numbers, but there is also a substantial stretch at 3300 wave numbers, corresponding to the strong and shorter sp hybridized carbon-hydrogen bond. Note also that there is a weak carbon-carbon triple bond stretch at 2126, which is visible in many terminal alkynes. Oxygen-hydrogen bonds in alcohols are shorter and stronger bonds than carbon-hydrogen bonds. There is also a larger difference between the mass of hydrogen and oxygen-16, which results in a higher frequency signal. In dilute solutions of alcohols, the OH stretch tends to come closer to 3,500 wave numbers. But for neat or pure samples, hydrogen bonding between alcohol molecules decreases the bond strength and increases the bond length, which shows up in a slightly lower frequency stretch. In 2-methyl-1-butanol, we also see sp3 hydrogen-carbon stretches, whereas in benzyl alcohol, we see both the sp2 hydrogen-carbon stretches and the sp3 hydrogen-carbon stretches. In more acidic phenol and in carboxylic acids, the OH stretch is broader and centered at a lower frequency. For a carboxylic acid stretch, it is not unusual for this broad band to cover 1,000 wave numbers. Compounds containing NH bonds also show stretching frequencies to the left of the carbon-hydrogen bonds, similar to the OH bonds. These also tend to be broad bands due to hydrogen bonding. For primary amides and primary amines, there are typically two bands. One is an asymmetric stretch for the NH2, the other is a symmetric stretch for NH2. The same for the amine, asymmetric at the higher frequency and symmetric at the lower frequency. Note in the case of the amide, there is also a carbonyl stretch at about 1680 wave numbers, and that will be discussed in a moment. This chart shows a large number of carbonyl compounds. As I mentioned earlier, there are two important numbers to remember in infrared spectroscopy, in addition to 3,000 wave numbers for the boundary point between sp2 and sp3 carbon-hydrogen stretches. Acetone and cyclohexanone have a carbonyl stretching frequency of 1715 wave numbers. And 1715 is the second number that you should know for infrared spectroscopy. Aldehydes and electronegative elements, such as oxygen, increase the frequency to higher wave number. Ring strain also moves the stretching frequency to higher wave numbers. The carbonyl has a higher bond order in both esters and in strained compounds. As the strain of 5 and 4-membered rings slightly weakens the carbon-carbon sigma bonds, that electron density goes into the carbonyl group, slightly increasing the bond order and strengthening and shortening that bond, hence the larger frequency. This is particularly pronounced for cyclic esters or lactones, stretching from 1735 for the 6-membered ring lactone to 1820 wave numbers for the 4-membered ring lactone. Electron withdrawing or conjugating substituents will move the stretching frequency to lower wave numbers. In the case of an aromatic group that is conjugated with the carbonyl, that slightly diminishes the bond order of carbonyl. Likewise, the nitrogen of an amide conjugates with a carbonyl, very slightly decreasing its bond order. This is a chart that is worth printing out and posting next to your local infrared spectrometer. These are representative spectra for acetone and cycloheptanone. The distinguishing characteristic is the carbonyl stretch at 1715 and just below 1715 for cycloheptanone, which is generally one of the largest peaks in the spectra, often relative to the carbon-hydrogen stretching frequencies. Occasionally, you will see some weak bands in the region for OH bonds. Those may correspond to small amounts of the hydrate of the ketone. These are spectra for acetophenone and acrylamide with carbonyl stretching frequencies slightly below 1700 wave numbers. This is the spectrum for the aldehyde octanol with carbonyl stretch at 1728 wave numbers. For phenyl acetate, the phenoxy group withdraws sufficient electron density to weaken the carbon-oxygen bond, and that strengthens and shortens the carbonyl bond, evidenced by the frequency stretch at 1771 wave numbers. Terminal alkynes will show a weak carbon-carbon triple bond stretching frequency around 2100 wave numbers. Carbon-nitrogen triple bonds of nitriles tend to give a weak absorption around 2250 wave numbers. I will conclude this video on infrared spectroscopy with an example from my own laboratory from a number of years ago. We synthesized the 6-membered ring carbonate, and in the infrared spectrum, this gave a stretch at 1716 wave numbers. By the way, there's also an azide stretch that's evident around 2100 wave numbers. We prepared this compound from the secondary alcohol formation of a mesylate in displacement with sodium azide. We then set out to make the diastereomer by the same route. But instead of forming the 6-membered ring carbonate, there was a rearrangement to give the 5-membered ring carbonate, which gave a carbonyl stretch at 1800 wave numbers. This experience, for me, exemplifies the value and the importance of infrared spectroscopy for compound characterization.